So we are going to start off Miss Kane and Miss Rothstein's Algebra 2 class for 12.1. We are going to define and use sequences in series today. So a sequence is a function whose domain is a set of consecutive integers if a domain is not specified, it starts at 1. So this is a pretty mathy definition. All that this means is that it's a list of numbers that come one after the other. So they'll map on to what we call a range, and the values in the range are called the terms of the sequence. So a domain gives the position of the term, and the range gives what that term is. So the first position of the term matches up with what we call the first term of the sequence, and we'll designate the term to use A, and we'll say A1 is our first term. So similarly, the second position, that second position maps with the second term, third with the third term, and so on and so forth, and we'll call this up till the nth term, which is any term that we want, and we'll say that maps to the nth term. So we're going to look at a couple of different sequences. Biggest thing to note here is that a finite sequence ends and an infinite sequence goes on forever, and a sequence can be defined by an equation or a rule. So a really nice exercise to kind of get us started with this is to write the first few terms of a sequence, and for both A and B here they give us a rule, and so we're going to write the first 6 terms. So for A, we are going to write the first terms of n plus 4. An is equal to n plus 4. So I'm going to start by saying what happens when n is equal to 1. That's going to be my first thing I plug in. So my first term happens when I plug 1 in for n. So I get 1 plus 4, which gives me 5. That is my first term. My second term happens when I plug 2 in for n. So back into the original, 2 plus 4 is equal to 6. So my second term is 6. Third term I get is 7. Oops, sorry. My fourth term is 8. My fifth term is 9. And then my sixth term, my final term that I'm looking at here, plug in 6 for n plus 4 gives me 10. Now, this is kind of a clumsy way to write all of this, so what we can do is we can just list out these numbers: 5, 6, 7, 8, 9, and 10. And those are my first 6 terms of this sequence right here. And similarly, we can do the same for B. So for B, I'll scoot over a little bit. We're going to start with n is equal to 1 like we did before. So my first term, don't worry that this is f of n. It's just saying that this is a function, not a big deal. If it makes you feel better, you can switch this to an if you would like. But I can say f of 1 will always start at 1 is negative 3 to the 1 minus 1, plugging in 1 for n because we're talking about the first term here. So what this is, it's negative 3 to the 0, which gives me 1. That's my first term. Second term, negative 3. Wherever we see an n, we're going to plug in a 2. Second term. Negative 3 to the first power gives me negative 3. If I plug in 3 for my third term, 3 minus 1 is negative 3 squared. And remember, if you plug this into your calculator, the negative 3 has to go in parentheses to give us a positive 9. And then similarly, the fourth term That will be negative 3 cubed, negative 3 to the 4 minus 1, which will give me a negative 27. The fifth term, negative 3 to the fourth, gives me a positive 81. And my sixth term, negative 3 to the 6 minus 1, negative 3 to the fifth, gives me a negative 243. So I kind of ran out of room here. So this goes with these. And then if I write out these lists of numbers, I'll have 1, negative 3, 9, negative 27, 81, and negative 243. Those are for that list of numbers. Those are the first 6 terms of each of these sequences. So really just plugging in and seeing what you get. These 3 here at the bottom, A, B, and C, are for you to do on your own. If you do them correctly, though, you should get this list of numbers. And we'll give you the answers, but the hope is that you do complete this on your own to get you your practice to get ready for tomorrow. So we get some alternating terms with this letter B, alternating signs. And for letter C, everyone's favorite, we get fractions.
All right, so what we are going to do now is we're actually going to take the terms and take this series, and we're going to create a rule like we talked about before. So if I look here, if the terms of a sequence have a recognizable pattern, then you may be able to write a rule for the nth term of the sequence. So pretty much what we're doing is we're creating an equation that will give me this sequence. So my first pattern here is 0, 2, 6, and 12. So here, my first term for A is 0. My second term is 2. My third term is 6. And my fourth term is 12. So we need to figure out how I can create this pattern. Well, if you look, it looks like I'm taking my 1 and I'm multiplying it by 0 to get my 0. My 2 could be multiplied by 1 to get 2. My 3 would be multiplied by 2 to get my 6, and my 4 would be multiplied by 3. So here, what we're really doing is taking the n term and multiplying it by the number before. So if I write a rule for that, it's going to be f of n equals, and I'm taking my term, my n, and I'm multiplying it by 1 less than it, so n minus 1. And if I plug that in, n, if I let n be 1, 1 times 1 minus 1, which would be 0, 1 times 0 would be 0. If I let n be 2, 2 minus 1 would be 1, n would be 2, 2 times 1 would be 2. So I have created a rule or a pattern for this sequence. Now for B, I would do the same thing. My first term is going to be negative 1. My second term is going to be negative 8. My third term is going to be negative 27. And my fourth term is going to be negative 64. All of these are negative. So if I look here, I'm going to have, so here, if I'm looking 1 to get to negative 1, maybe I multiplied by negative 1. 2, there's nothing I can really multiply by, so now I need to think about raising it to a power. Well, since all of these are negative, when I write my rule here, I think that I'm going to have a negative n value, and it has to be raised to an odd power in order to keep it a negative. Well, 2 raised to what power will get me 8, and 3 raised to what power will give me 27, and 4 to 64, well, that would be to the third. So if I did negative 1 to the third, that's going to give me negative 1. If I did negative 2 raised to the third, that's going to give me negative 8. Negative 3 raised to the third, that's going to give me my negative 27. And you see here that I have created that rule. So for the next two, A and B, I'm hoping that you're pausing this video and trying these on your own. So for A, you should have gotten A n equals negative 4n. And for B, remember it doesn't matter if you write f of n or a of n, however you want to write it. A of n equals n squared plus 1. And I'll do one more example with you just to make sure that we are on the same page here. For a sequence of 3, 8, 15, 24. So once again, my first term is 3, my second term is 8, my third term is 15, my fourth term is 24. Okay, so now if I look to go from 1 to 3, so maybe I multiplied by 3 here. 2 to 8, I'm going to multiply by 4. 3 to 15 multiplied by 5. 4 to 24 multiplied by 6. So what I'm doing is I'm multiplying this number by 2 numbers ahead of it. So when I write my rule, A of n equals n, I'm multiplying my n by n plus 2. So if you look here, if I were to plug 1 in, 1 plus 2 is 3, 1 times 3 is 3. That gave me my first term. When n is 2, 2 plus 2 is 4, 4 times 2 is 8. That gives me my second term. A lot of the times you just need to try to look at the pattern and figure out what you are doing here.
So we talked about this on the first page. So when the terms of a sequence are added together, the resulting expression is called a series. Now, we mentioned what a series was, but we only talked about what a sequence was, but the same rules apply with finite and infinite. So a finite series is a series that ends, and a series is just a list of numbers that are added together. So like 2 plus 4 plus 6 plus 8, it's a finite series. And an infinite series goes on forever. So we can say 2 plus 4 plus 6 plus 8 plus forever and ever. Now, this is kind of a clumsy way of writing, this clumsy way of notation. Math people do not like to write things this way. We like to make it nice and condensed and neat. So we'll come back to this super quick. But I want to talk about what we call summation or sigma notation. This is on your third page here. So what we will have is we have this big E. Looks like an E. It's Greek letter sigma. And what this means is it means to sum, or for our purposes, add up. And this bottom part, we'll start with the bottom first. This tells us the lower term, or the first term. We'll say first or lower term. And the top part tells us the last term, where we go up to. And like I said, so we have some rule here that we would follow, we would plug in. So this goes back to the second page here. So if I have this finite series 2 plus 4 plus 6 plus 8, I would create in sigma notation, big fancy E. I am starting with a first term. So I'm going to say my I is equal to 1. Now, we're not really going to deal with any situations where it doesn't start with the first term. That's a little beyond what we're going to do in this classroom. But it does happen, but we're not going to experience that. This is the first term, and I end with the fourth term. First, fourth. So I'm going to end at 4. And it's really important to note here, I don't have 8 up here. I have what term it is. It is the fourth term. This is the first term. And now we've just got to create our rule. So similar to the previous page, I'm going to say my first term is 2. My second term is 4. My third term is 6. And my fourth term is 8. So this is a pretty straightforward rule. Hopefully you can see it. So I get from 1 to 2 by multiplying 1 by 2. I go from 2 to 4 by multiplying 2 by 4. 2 by 2 to get 4. I multiply 3 by 2 to get 6. I multiply 4 by 2 to get 8. So my rule, I can say, is 2 times the number of term that I have. 2 times n. Now, this is a picky math thing that math people get picky about. This I and the essentially variable that goes inside here have to match. So I'm not going to write this as 2n. I'm going to write this as 2i so that these guys match. If you wanted to write this as n is equal to 1 and 2n up here, that would be fine as well. It's just proper form, good notation. We're teaching you to be good math people. So that's for a finite series. For an infinite series, it's the same set of numbers, so I'm not going to do too much different here. The rule's still the same. I'm still starting with the first term. That's my first term. Now, but I don't end, ever. It just goes on and on and on and on and on, forever and ever. So at the top here, my last term, I am going to put an infinity symbol, and that tells me that this series is infinite. It doesn't end. We start it with the first term, and it just goes on forever. Now, I have a couple examples here that I'm going to go through with you. So, first thing that we're always going to, easiest thing to do is to draw the E and say where we're starting and maybe where we're ending. This one, maybe where we're ending is going to be a little bit more difficult. But we are starting with the first term. So I is equal to 1. Now, I have a little break here, but I do have a last term. But I don't know what n this is. I don't know what number of term that is. So maybe I should create my rule first. So let's see if we can do this. My first term is 25. My second term is 50. My third term is 75. And some term here is 250. So we're going to only have to be able to rely on these 3 terms here to figure out what the rule is. So 1 to 25, I can get there by going 1 times 25. That's pretty straightforward. 2 to 50, I can get from 2 to 50 by doing 2 times 25. 3 to 75, I can get that by doing 3 times 25. So what I find here is that this pattern, it's going to be 25 times whatever number of term I have. And like I said, for consistency purposes, we'll use I because we chose I as our little variable, as our index. That's what we call it. So, this is my rule. And the only thing I have left to do is find out where I stop with this 250. So if my rule is 25i, I want to know what I gives me 250. So like a little mini algebra problem we have here. We can divide both sides by 25, and we'll get I is equal to 10. So this is my 10th term. For people who are really good at recognizing patterns and you wanted to list this out and see where you can get to 250, that would have been fine as well, but you can do a little mini algebra problem to figure that out. Alright, now to the fractions. Okay, same thing. We'll start with big sigma because that's pretty nice to start with. We start with the first term. This is the first term. And we end with the fourth term. So that is my end point. Okay, so now we've got to deal with the fractions. So my first term is 1 over 2. Well, that's not very helpful. My second term is 2 over 3. My third is 3 over 4. My fourth is 4 over 5. Now, with fractions, what we're going to want to do is look at the top and look at the bottom, look at the numerator and the denominator, and see what's happening in both of those instances. Is there something different happening? Is there a rule different from the numerator and the denominator? So what I find here is that my numerator always matches up to whatever term I have. So my numerator, I'm going to go to I, because I'm going to put I in my equation. My numerator matches up with I. So I'll say this is my rule. F of n is equal to the numerator, which is whatever term I have. And the denominator is always 1 plus whatever term I have. And I can say the denominator can be written as I plus 1. And I can just write that as my rule. That will work out just fine if you test it out. Say, all right, the value of 3, whatever that rule is for 3, if I plug in 3 for I get 3 over 3 plus 1, which is 4. So I have 3/4. Wait, I want to write that there. So I'm going to say I over I plus 1. Ignore that. So that is my rule. That is my rule for my summation notation. That's how I would write this series in summation notation. And then finally, let's do this last one. Same idea. Actually, same idea as letter A, where we have some endpoint, but we don't know what term that is because we have these little ellipses in the middle preventing us from knowing that. So I'm going to say I is equal to 1 because I have my first term here. I don't know what that last term, I don't know what 729 is. So I'm going to have to rely on my other terms to help me get there. So listing them out. Now, a couple patterns you should know. Definitely squareds. Definitely, can you see that you're adding 1 or adding 2 to whatever term that you're looking at. But the cubes are pretty common as well. So, and we already saw the cubes on the previous page. 1 to 1 doesn't really give me anything. 2 to 8, you can say that you're adding 6, but you're not adding 6 here. You're definitely not adding 6 here. So these rules follow the cubes. 1 cubed is 1. 2 cubed is 8. 3 cubed is 27. And 4 cubed is 64. So I'm going to say my rule, my a sub n, is equal to n cubed. Or if I'm going to write it with the I put the I cubed here. Now, I just got to get what this last term is. So, I'm going to say, little mini algebra problem here, I cubed is equal to 729. So if I want to get what that last term is, I'm going to cube root both sides to get what I is. And I get I is equal to 9. So that is my last term. 729 represents my 9th term. So these are a couple of ones that you guys hopefully can do on your own. To pause the video and take a couple shots at it. There is a fraction one in there for you to mess around with. Pay attention to what's happening in the numerator and what's happening in the denominator. Now, it may take you a couple of tries to see what's going on for pattern recognition. So maybe you see the rule after we write it and you kind of work backwards and see if you can get that or see where we get that from. So for my rule here, I end up getting, my lower limit is 1, and my upper limit is 20, and my rule is 5 times I. So hopefully you can get that one. This one, a little bit trickier. It is an infinite series, so we got that infinity sign up top. Oops, this is an I, not a 1. This is actually 6 to the I power, so a little tricky for you guys. And then this last one, this rule, we end with the 4th term, we start with the 1st term, and then the fraction, we have a different rule for the denominator and the numerator, the denominator. And that's the rule that we can have. So those 3 are the answers for those 3 summation problems. Like I said, if you're having trouble kind of getting it, maybe you take a look at what I got here and see if you can work backwards and see if you can generate that. This will take a couple tries to get it, to kind of get it right.
Alright, so one thing that we want to note is that the lower limit does not have to begin with 1. So we want to make sure that we look at where the lower limit is starting, and that's where we start from. So in these next couple examples, we're actually going to find the sum of the series. So if I look at this first example here, notice I'm starting when k is 4, and I'm going to the 8th term. So I'm starting at the 4th term, and I'm going to the 8th term. So here, all I'm going to do is plug 4 in for k. So it's going to be 3 plus 4 squared plus 3 plus 5 squared plus 3 plus 6 squared. So this is my 4th term, my 5th term, my 6th. 3 plus 7 squared, and one more to give me 3 plus 8 squared. Okay, so 4th term, 5th term, 6th term, 7th, all the way up to the 8th term. And then from here, this is easy plug and chug. All I need to do now is find these values. So this is 19 plus 28 plus 39 plus 52 plus 67 to give me a grand total of 205. All right, and then if I look at my second one, notice here now I'm starting at the 3rd term and I'm going to the 7th term. So all I'm going to do is plug 3 in for k, and I'm going to go all the way up to 7. So this is then 3 squared minus 1 plus 4 squared minus 1 plus 5 squared minus 1 plus 6 squared minus 1, and finally plus 7 squared minus 1. Same thing here. All I have to do now is figure out these values. 8 plus 15 plus 24 plus 35 plus 48 to give me a grand total of 130. So I'm hoping maybe that you'll pause and try this next one on your own. If you don't, that's okay. We'll have more practice for you tomorrow. But here, now I am actually starting at the first term. I'm going to the 6th, and my rule is just n. So this is just 1 plus 2 plus 3 plus 4 plus 5 plus 6. When I add those up, I get 21. Okay. So let's focus and look for one more second at the bottom.
Okay, so the bottom are what we call special series. You don't need to memorize these, which means I hope that you don't automatically put this out of your head. But it's going to be kind of helpful if you have this almost as a reference. So might be helpful tomorrow on your worksheets or on reviews just to have them handy, because they're kind of cool. So what this first one says is the sum of n terms of 1. So this doesn't make any sense. But it's saying, all right, if I add up 1 n times, from 1 to n times, what will I get? And you will just get n. So that's what it's saying. It may not make sense in this format, but it's saying if I add up 1 n different times, I will get what n is. Now this one is actually kind of really neat, and this is really somewhat powerful, I think. So it's the sum of the first n positive integers. So it's saying if I add up any number, or if I add up a number from 1 to whatever, what do I get? So if I wanted to add up the numbers 1 to 100, what would I get? 1 to 500, 1 to 1,000,000, what would I get? So this is kind of cool. And what you end up getting, the rule that you have is n times n plus 1 over 2. So very cool. We actually saw that up here with this problem. We said, okay, I said we have n is equal to 1. I'm going to 6, and it's just n. These guys match. So just to kind of hammer the point home a little bit, if I follow this rule, except I just do this instead of this, what I'm going to get is I'm going to get 6 times 6 plus 1 over 2. So 6 times 7 over 2. 6 times 7 is 42 over 2. which is 21, smiley face, we did it, it works. So just something that's very cool, very neat that happens. And then the last one we have, this one's a little bit more complicated than this one. It's the sum of the squares of the first n positive integers. So if I start at 1, if I add up 1 squared, 2 squared, 3 squared, 4 squared, so on and so forth, what would I get? So this rule is the following. N times n plus 1 times 2n plus 1 over 6. So like I said, nothing that you need to memorize, but it might be just good as a reference piece as you're going through some assignment, worksheet, review, something like that, just so that you have it handy. But that's it. We will work on our worksheet tomorrow in class, and come in with questions if you have any.
Thank you.
Thank you, guys.